So the first thing that is really good about gaseous hydrogen is that it is not toxic, right? It's not an irritating gas, it's non-poisonous gas. However, hydrogen doesn't support life. And what I mean is that if hydrogen gas presents in a very high concentration, it can be an insufficient. And what I mean is that when you have a hydrogen leakage in, say, an enclosed area, then hydrogen can displace oxygen and reduce the concentration of oxygen in that kind of enclosed area that you're in. So for example, in our normal atmosphere here, the oxygen concentration is about 21%. The remaining 78%, 79% belongs to nitrogen and other trace gas. So that is the normal kind of condition or the normal oxygen concentration that we are, familiar with and can live with. However, if that oxygen level drops, then it would lead to a number of different kind of consequences depending on the level that you're at. So the alarm normally being placed for oxygen detector is at 19% level because anything between 19 and 21% or even higher wouldn't cause any recognizable symptom or impact on human. But as long as you reduce this oxygen concentration in our surroundings below that 90%, then depending on that level, you will see on the table here different consequences that can happen to you. And more importantly, if that concentration of oxygen in the surroundings below 12%, then you can lose consciousness without any prior warning, like right away immediately. So this is, I guess, a very little level of oxygen concentration. However, keep in mind that anything below 19 should be used for alarm purposes. So you should be alarmed when the oxygen concentration level drops below 19% already. In terms of odor, color, and taste, pure hydrogen is odorless, colorless, and tasteless. So when you have a leak of hydrogen stream during daylight, it is almost impossible to detect it. You can't detect it by your naked eye. So unlike other hydrocarbon, for example, nitric gas, where you can actually add some odorant, for example, mercaptan with the chemical structure I show you on the right hand side to help you detect when there's a leak happen. When it comes to hydrogen gas, adding these odorants is not feasible. The first thing is that these odorant, for example, mercaptan here, have sulfur in it, and it can poison the fuel cell that is used to convert hydrogen to produce energy. But even if you use hydrogen in an application that doesn't require fuel cell, adding these odorants might not work well either. The reason is because hydrogen is really buoyant and it have a very high diffusion coefficient to a point it can move away from the leak much quicker than the odorant. So it kind of defeats the purpose by adding the odorant in, knowing that your hydrogen gas can be diffused much faster than what you added in. So we've been talking about hydrogen diffusing very quickly away. So I want to put some number on it. And I'm going to start with some density value and the related measurement of related measures of gaseous hydrogen. Again, these are related to the normal temperature and pressure condition. So gaseous hydrogen at MTP condition would have a vapor density of 0.0838 kilograms per cubic meter. So this is specify how much mass would be contained per unit of volume, in this case 1 cubic meter of volume. If you inverse that number, you would receive the specific volume of hydrogen, which is close to 12 cubic meter per kilogram. And what I mean is that this is the volume that would occupy if you have 1 kilogram of gaseous hydrogen. So you take the density of hydrogen up there, so 0.0838 kilogram per cubic meter, and you divide it by the air density, then you would receive the specific gravity, which is close to 0.07. And what I mean is that by doing so, we can see that, okay, the density of gaseous hydrogen actually is about 7% the density of air, or in the other words, hydrogen is 14 times lighter than air, right? So it makes sense that if you want to use hydrogen for any practical application, the first thing you need to do is that you need to compress hydrogen or even liquefy it so that you can increase its density to make it easier to use. Due to its lower density, hydrogen, as I mentioned before, is really buoyant. The buoyant velocity of hydrogen in air can reach up to 9 meters per second. Because of that high buoyancy, it actually can help hydrogen to be diluted very quickly, and help to reduce the concentration of hydrogen in the surrounding to be below the lower flammability level, which is 4 volumetric percentage. Again, I come to that later when we talk about the chemistry property of hydrogen, but at the moment, just keep in mind that due to its higher buoyancy, it is actually the main safety asset of hydrogen, so that when the hydrogen is released, it would rise and disperse quickly, and its concentration would be reduced so much quickly to even below its low flammability level. So for any application that is outdoor or in unconfined areas, then there would be a very different kind of approach or safety consideration to hydrogen accident compared to other flammable gas, for example, gasoline, simply because the high buoyancy of hydrogen already have in reduce its flammability level. Hydrogen also highly diffusive and have a very low viscosity. And what I mean is that hydrogen is prone to leak because it's too small, the small size of the molecule. It can even diffuse in small amount through intact material. And when it leaks, it's going to leak at very high flow rate through filling, sealing, and interior. Hydrogen itself is not corrosive, but its interaction with other metal can embrittle some of this material, causing the deterioration of the metal mechanical properties. And the last point I want to emphasize on the gaseous hydrogen is the Joules-Thomson effect. The Joules-Thomson effect refers to the change in temperature that accompanies the expansion of the gas without the production of work or transfer of heat. So if you look on the right-hand side here, what I want to say that for each given pressure, a real gas has what I call an inversion temperature, where there's no change upon expansion of the gas. And if you have multiple pressure values, you would have multiple temperature value, which eventually would form what you know as the inversion curve. And for the majority of the gas, at ordinary temperature and pressure, they normally cool when they expand from high pressure to low pressure. However, when it comes to hydrogen, it's a different story. So I choose another graph. We kind of zoom in a little bit in the Joule-Thomson effect of hydrogen. And you can see that at atmospheric pressure, which is about 0.1 megapascal here, the inversion temperature of hydrogen is 193 Kelvin, which is essentially minus 80 degrees Celsius. So, at the normal temperature that we are here, like let's say 20 degrees C, the expansion of hydrogen from higher pressure to lower pressure will not reduce the temperature. In fact, it would increase the hydrogen temperature. And for that reason, in the past, there was a bit of worry about, okay, increase in temperature would lead to hydrogen explosion. However, it is not the case, because even if you have an expansion from, say, 100 megapascal to the atmospheric pressure of 0.1 megapascal, the rise in the temperature of hydrogen went only from 300 Kelvin to 46 Kelvin, from 300 to 346 Kelvin. So rise of 46 degree Kelvin alone is not sufficient to be the source of ignition for a hydrogen or air or oxidizer mixture. And again, we touch base on that later when we're talking about the auto ignition temperature of hydrogen, and you would understand why such rise in 46 degree is basically just not enough. So with respect to liquid hydrogen, right? So I want to mention that when you be able to bring hydrogen to the liquid phase, then the hydrogen or the liquid hydrogen density in this case would increase greatly from 0.083 kilogram per cubic meter, in the gas stage, down up to 70.78 kilogram per cubic meter is the density of liquid hydrogen. The specific volume is 0.014 cubic meter per kilogram, and the specific gravity of liquid hydrogen for liquid water density of 1,000 kilograms per cubic meter is normally used as a reference, compared to if you're talking about specific gravity of gaseous hydrogen or of gas, then the air is normally used as the reference point. So in this case, for liquid, water density is used as the reference, and the specific gravity of liquid hydrogen, meaning that it is 70%, the density of liquid hydrogen is 70% the density of water, or in the other words, liquid hydrogen is 14 times less dense than water. So I think it's really easy to remember that, okay, if you have gaseous hydrogen, it's 4 times lighter than air. If you have liquid hydrogen, it's 4 times less than water. So we talked about before about the normal boiling point of hydrogen. So it's really low, 20 Kelvin here, corresponding to minus 253 degrees Celsius. What I mean is that liquid hydrogen at the temperature is basically a cryogenic liquid. So it has all of the potential hazards associated with cryogenic burns, for example, frostbite or hypothermia, or even lung damage if you inhale all of this cold vapor. So care have to be taken when you are dealing with hydrogen, and of course you have to have your PPE, like appropriate PPE if you are handling hydrogen. So that was just a very kind of basic handling of hydrogen, but you need to also keep in mind that the majority of the gas, with the exception of helium, when exposed to liquid hydrogen, will be condensed and solidified. So when that happens, the solidified gas can jam your valves, plug the pipe and orifice due to the ice formation. And another implication that if you have cold hydrogen being transported into, and if you don't have sufficient insulation, then it can cool the surrounding to a temperature below 90 Kelvin. Now, 90 Kelvin is an NBP value, or the normal boiling point value of oxygen, right? What I mean is that if you cool down the air below that temperature, 90 Kelvin, then you would end up with a condensate, like, kind of liquid form that have oxygen enriched, can go up to 52% volumetric percentage. And what I mean is that when you have such oxygen enriched environment, then you also greatly enhance the material flammability and combustibility. Very dangerous. So you have to be aware of that. And if your equipment cannot be well insulated, you have to make sure that the underneath of the equipment should be free of any organic material to avoid any flaming, and any chance of flame and combustion to take place. Another key point you need to be aware of when you're dealing with liquid hydrogen is the liquid to gas expansion ratio. So if you look at the figure on the right side, it's a visual representation of how a volume of liquid hydrogen would change after it has been expanded into the gas state. If you have liquid hydrogen released in a confined area and don't have an appropriate kind of venting mechanism, then such expansion ratio, 1 to 848, would be able to result in a final pressure of, excuse me, 177 megapascal. So when you reach a temperature guarantee, a lot of vessel would be ruptured, and that would cause a devastating effect, and explosions can happen just due to that large expansion ratio. So the consequence, as I showed it here, would lead to overpressure of your vessel, or even lead to the penetration of liquid hydrogen into the transfer line or the vent line to your system. So what I mean is that when you're dealing with liquid hydrogen or even cold gaseous hydrogen, you need to have appropriate ventilation or even pressure relief device so that you can prevent the overpressure resulting from the expansion of hydrogen either in liquid stage or cold gaseous hydrogen. So even when you handle it chemically, you have to know that the liquid. Sorry, go by your step, right? So when it comes to liquids in spin, you have to be aware that if the liquid hydrogen leak occurs, then as we mentioned before, it has a very low normal boiling point, 20 Kelvin. The temperature would be so low that it would condense the air and the vapor in the surrounding area, and it would create a visible cloud when the liquid hydrogen is leaked. So because of this low temperature, where the vapor is heavier than air, then you can see when liquid hydrogen is released, it would initially flow horizontally or even downwards. But as the temperature of the cloud of the vapor warms or increase, the cloud is just going to be dissipate and quickly rise. But you have to be aware that if there's a liquid hydrogen, it can also pose potential fire hazards if it mixes with air during such a leakage or spin